My name is Malvina and this is Diego, and today we're here to share with you a war story, and it's the war story of how the low-latency real-time news search engine at Bloomberg was tamed in order to learn how to rank. So Diego and I are both software engineers at Bloomberg for the last 2 to 3 years. We work on the news search experience team at Bloomberg, which means that our job is to make sure that all 325,000 clients using the Bloomberg terminal to find news are happy with the search experience they have, which means they can find relevant content and they can do that in the blink of an eye. So before joining, Diego and I came from slightly different worlds. So I was doing a PhD in machine learning and statistics. He was working on information retrieval. And we've kind of since merged forces in order to get learning to rank working in production. So you probably know Bloomberg from maybe the news channel, but we're much more than that. Bloomberg is a global technology company operating in the financial domain. And our mission is to bring transparency to capital markets. And we do that through our main product, which is the terminal that you can see on the screen, which basically provides financial data, analytics, communications, and trading tools to more than 325,000 clients across the world. We provide lots of different types of data to our clients, but one of the most important data types that we provide is news. And this is where the Bloomberg News search engine comes in. Every day, we ingest more than 2 million search stories from many different sources. At peak time, we could be ingesting more than 500 stories per second, and we keep an index that's about 650 million stories. We serve more than 16 million search requests per day, and we have an average query response time that's under 200 milliseconds. And you can think that when you're trying to do machine learning in the space of those 200 milliseconds, it's not really a walk in the park, and that's kind of the theme of today's talk. So before we start talking about machine learning, let's take a step back and think about how we can get relevant results for our users without using machine learning. So at the simplest level, you take your favorite search engine, you type in a query, and that query could be matching thousands, even millions of documents in your inverted index. So how do you find the most relevant documents to return to your user? So this is where relevance functions can come in. And the idea is that you use these relevance functions to assign scores to each matching document so that you can then sort by relevance and return to the user the results that are most likely to meet their information need. So how do we design these relevance functions? So at the simplest level, if you have, say, a single query term, what you can do is to look at how often the query term appears in the document and then assign a relevance score that's proportional to that. Once you do that, however, you probably realize that actually some fields in your document are more important than others. They're more telling of how relevant your document is. So you might want to boost certain fields more than others, so say the title or the short snippet description. So at that point, how do you actually decide which fields are the most important ones and how much you should be boosting them? So you probably can start maybe hand-tuning these relevance functions, and I hear that people actually do that. But maybe you can get away with doing that for a few queries, but then you get a bunch of other queries, and product is maybe complaining that relevance isn't really working for those kinds of queries. And then maybe you realize that actually the term frequency is not good enough to tell you whether something is relevant. So you start looking at other aspects of the document, say how fresh the document is, how long, how popular, who the author is, and so on. So how do we consolidate all of these different signals, and how do we fix the relevance for many different queries? So first of all, we don't sit down and hand-tune relevance functions because I don't think that's our job. And this is where machine learning can come in. And this is how we can use data to train algorithms to distinguish relevant from irrelevant documents. And that's akin to how you would train an image recognition system to maybe distinguish between pictures of pedestrians and cars. So what our team is most excited about is this achievement in 2018, which is deploying learning to rank fully to production. So how many of you have used the learning to rank plugin in Solr? OK. How many of you have used it in production? OK, a couple of hands. Maybe you share some of our pain. OK. So for the uninitiated, learning to rank basically means using machine learning to train algorithms to rank results in a way that optimizes search relevance. So how does this work in practice? So let's start with what we're probably all familiar with. So you have your index in just different types of documents. A query comes in, types in a search. We find all matching documents in the index, and then we apply a relevance function that's...
Sorry, anyone that's standing doesn't need to exit the room in spare capacity, so if you need to seat, you do need to. There's no sitting, no standing. We need to have everyone out that is not in a chair.
Can we find a bigger room? This is obviously a popular session.
Yep, we will let them know, but for now, for everyone's safety, we should have people that don't have a seat out.
We can repeat the talk later.
Doing the session for us.
Yeah. Yeah. Okay. Yes. Not sure. Okay, so I'll try again. Right. So user types in a query, it matches, you retrieve all matching documents, and then you can apply a relevance function. So maybe something simple that like I showed before, maybe TF-IDF, BM25, retrieve the top K documents. Say, so if you're doing learning to rank, then we add 2 more steps. So first of all, in the first step, if you want to return 10 results to your user, rather than ranking 10 results, you're going to rank 100. And then you're going to take these 100 results that you've top ranking results, and then you pass them to the re-ranking model. The re-ranking model is your learning to rank model. And the idea is that this is something much more complex than the first relevance function we had. It could be something like a neural network, a lambda model, support vector machine. But the idea is that it's something that's much more expensive to compute, so we don't really want to apply it to all matching documents. We apply it to kind of a curated list of candidates. And then once we do that, we get new relevance scores, we rank by that, and return top 10 results to our user. So Diego now will take over, and he'll tell you more about how the Learning to Rank plugin works in Solr. And then we'll make this more entertaining, because we'll tell you about all the things that went wrong when we tried to use the plugin in production.
Thanks, Malvina. I hope I'm using this in the right direction. This one? Yes. OK. So I'm now going to review all the steps, all the things that you need in order to ship a Learning to Rank model in production. So the first step is that you need data. Okay? So the first thing that you need in order to train a Learning to Rank model are examples. So the first thing to do is to collect judgments. Learning to Rank framework works that you need some examples, and examples are formed by a set of queries. So you select a set of queries that are important to you, and then for each query, you need to know which are the relevant documents and the not relevant documents. And the way you do that is by collecting judgments. So in this example, we have a particular query that is the ticker symbol of Apple, and we have some matching documents. The first one is a page about Tim Cook from Wikipedia. The second one is the Apple ticker description by Bloomberg. The third one is a page about Apple seeds that is clearly not relevant. On the right, we have judgment that comes into different flavors. We can have binary judgments, so just is the document relevant or not, or we can have score judgments that are give me a score from 0 to 5, tell me how much the document is relevant for the query. Judgments are better because they give a ranking, so they give it the exact order that the document should show. How do you get these judgments? Easy. You can ask people in your company to sit down, look at the documents for your query, and tell you which are relevant in their opinion and which are not relevant. or you can hire some expert to do that for you, or you can do bigger and you can use crowdsourcing. So there are websites on the web that allows you to set up jobs where people on the web can annotate your document. This is quite expensive to do. You need to spend many hours doing that. But what you obtain at the end is high quality data that you can use to train your learning to rank model. The other way is by using implicit signals. So if you don't want to spend all this time annotating document and you have a service with users, you can rely on the interaction of your user to create the data that you need to train the model. Because if you have, if you are selling some product and your user is searching for something and then click on a particular product and buying it, it's giving you a signal that that particular document was relevant for the query. While if, for example, is clicking on the second product and is completely ignoring the first one in the ranked list, it's also telling you that the first document was not relevant because it completely ignored it to click the second one. So by analyzing this interaction, you can obtain a good training set. The drawback here is that usually this data is very noisy, so you can get more data, but it's more noisy. You have to spend time cleaning it, and sometimes it's not enough because it's so messy that you can't really extract any insight from that. So once that you have your training set, the second thing to do is getting features. So these are the signals that Malvina was talking about before. So a feature is just a number that will tell you something about your document. It tells you about a particular characteristic of the document that might be correlated with the relevance. So in this example, we have if the query matches the title, the freshness of the document. For us doing news, this is a very important signal, as you can imagine, because if a news is from yesterday, it's for sure more important than a news from 3 months ago. If it comes from Bloomberg.com, the popularity, that might be the number of views that the story got in the past, and so on. So the idea of learning to rank is that instead of just looking at trivial scores like the 10 frequency, we can get all these signals together and learn how to combine them to produce a new score that will tell us more about the fact that the document is relevant or not. So the way it works when you train a model is that you produce this feature, and for your training set, you produce this feature and you connect them with the fact that the document was relevant or not, and then the trainer will learn how to combine them. So in order to train your model, the thing that you have to do is to produce the feature for your training set. How do you produce feature with Solr? The first thing is that you need to describe your feature in Solr if you want to use the feature in Solr. And the way you define a feature is by using a JSON snippet. So in this case, we have the feature that I showed in the example before. And each feature is just a JSON snippet that has a name, the name of the feature, a type that will be a Java class that tells Solr how to compute that particular feature, and some free parameters. In this example, we are using a particular type of feature called Solr feature that is available in Solr that allows you to reuse the Solr query language to compute the score, the value of the feature. The value of the feature will be just the score that the query assigned to that particular document. So for example, here in match title, we just check if the text of the query, the score of the text of the query in the field title. In freshness, we are using a function query that goes into the timestamp and compute the difference with the current time, and so on. So often you can just use this type of feature to describe all your feature. If you need more, you can still go into Java and implement your feature and use it into the plugin. Once that you have your JSON file, you can just upload on Solr by using a card command, and that will make it available for Solr to compute. As I said before, in order to create your training data, you need to process your document with a query to produce the feature for your document. So in Solr, there is a way to do this, and is by using a doc transformer. Doc transformer is something that is unrelated to learning to rank. It's a feature of Solr that allows you to add virtual field to each document, and the learning to rank plugin provides a special doc transformer called the learning to rank feature logger transformer. And you use it just by adding this line to the Solr config. And then you can just ask for a special field called features when you perform your query. And then Solr will add a special field to each document that contains the list of the feature for that particular document. Okay? So by using this, you can take all the queries in your training set, generate the feature for each document, attach them to the label that will tell if the document was relevant or not for the query, and train a model. So next step is training a model. Once that you have your file, you can just feed the file to the trainer, and the trainer will try to learn how to combine these features together in order to maximize, to predict the right label. There are a lot of different ways to train your model. Here we gave 2 examples. One is RankSVM. The other one is LambdaMart. RankSVM is a linear model. So it's kind of more simpler. It just learn a simple combination of the feature. Here there is an example. So this is a kind of model that you can learn with RankSVM. You just learn the weights for your feature. So here we can say like multiply 1.2 for the value of match title, add 10 multiplied for the popularity, and so on. So this is a very simple model. So it can be effective. You can do more complicated things. You can say things like, if match title is greater than 3, then look at the popularity. If the popularity is lower than 3, then look at the freshness, and do all this kind of reasoning that is more complicated and it is not linear. And that's the type of thing that you can do with a model like LambdaMart that is more powerful. Once that you have your model, once that you have your model, you can encode the model in a JSON file, like for the features. So you will have, in the JSON file, you will have the class that describes your model. So you can have a linear model, you can have a non-linear model, and then you will have a name that identifies that particular model, and then the description. In this example, we have a LambdaMart model that is composed by a forest of trees. So here in the JSON, we have encoded a forest of trees. Again, as for the feature, you take your model in JSON, you curl it on Solr, and then you can use it to rank your document. How do you do that? You just add a query parser, a particular query parser, the LTR QParser plugin. You give it a name, LTR, and then you can just use in your query. So you just type your query as usual, but then you add this particular parameter, RQ, that stands for rank query, and you call the LTR query parser, and then you give the name of the model that you want to use and how many documents you want to re-rank. Okay? So once done that, we are in business. We can re-rank the documents using our model. The last thing that you really want to do is to evaluate your model. Okay? It's important to have metrics on how you're doing, because you could have made an error, your model could not be that good, so you want to know how it's doing. And so there are many, many metrics to do that. Here there are some. Precision is one of the most used metrics. It's basically telling you how many relevant documents you are returning for your query. So if you are returning to your user 10 documents, and only 5 are relevant, your precision will be 5 divided by 10, 0.5. If all the documents are relevant, your precision will be 1. It will be good. Recall measure how many relevant documents you're returning over all the relevant documents in your collection. So if you're returning 5 relevant documents, but in your collection you have 500 relevant documents for your query, your recall will be 1%. And finally, NDCG is normalized discounted cumulative gain. This metric is used a lot when you do ranking, and it basically tells you how good is your ranked list. So it doesn't look at the set of relevant or not relevant results, it looks at the order. This is very good because if you look just at the precision, if your 5 relevant documents are at the head of your list or at the bottom, your precision will be the same. But if you use NDCG, you will get different NDCG. If they are at the top, then NDCG will be 1. If they are at the bottom, will be something lower, 0.6, for example. Okay? So now that you have your metric, you can check that your model is doing better than the previous ranking function and tuned that you had before, and you can ship it to production. Okay? So this is the point where I let Malvina speak. We were at this point, and we had to ship our model that was good with the metrics in production.
Okay, so now started the fun bit. So around May 2017 last year, it seemed that we were close. We had all the infrastructure bits ready. We felt that we were close to having the first machine learning ranker in production. So at that point, we had a placeholder feature store that was logging features in production. But it wasn't really computing useful features. They weren't really things that we could use to actually train a good model. So we sat down with product, and we came up with a list of features that we thought would help us decide whether something was relevant or not. So we implemented those features, deployed the new feature store, and we waited for magic to happen. Instead, we got this. So the green line was the well-behaved feature store that wasn't very smart. And then the white line was what happened to our search latency when we deployed the new feature store. So at that point, we were kind of frustrated. Why was it slow? Which feature was slow? So the biggest problem we had at this point wasn't even the speed. It was the fact that we didn't know what was going wrong because we didn't have analytics to see which features were taking the most time. So we took a step back, and we instrumented support in Apache Solr to log the time it took to compute each feature on each document, and we changed the LTR feature logger transformer to return that in the response along with the feature values. And then we added our analytics on top of that, and so we could start from somewhere. So we started looking at the feature latency, so the time it took to compute features across documents with the first feature store. So we were taking something like 15 milliseconds. So that was OK. As soon as we deployed the new feature store, we were taking 145 milliseconds. So it was almost 10 times slower. What was interesting here was that when we actually looked at the distribution over the feature latencies, there was one class of feature, which I'll call the sloth feature, that seemed to be taking systematically a lot of time. So at that point, at least we knew what the problem was. So we went in and we looked at the code of that feature. We optimized it, reincarnated into the fast sloth feature. So we were now taking 19 milliseconds to compute features for 10 documents. So overall, we're taking a bit less than 2 milliseconds to compute features per document. And that's kind of OK if you want to compute features for, say, 10 documents. But if you want to do this for 100, and if you also want to have room to add more features, then that doesn't really work. So how could we go faster? So we sat down and we thought about this. And what was evident was that some of the features that were taking a lot of time were actually static features. So they were features that didn't really depend on the query. They were of the type, is the query a reliable source? Is the author X, et cetera. So what we could do is pre-compute those static features and store them in the index. So we did just that. So we went to the Solr schema, and for each of the static features we added a new field. And then we changed the update request processor chain in Solr, which is a chain of events that gets executed on every single update request to compute the new fields from already existing ones. So we basically moved the feature computation logic in custom update request processors. So in the snippet of code, I basically have this custom update request processor that will look at the wire field in the document for a specific tag, and if that string is present, it will write a value of 1 to that feature and 0 otherwise. And you can do that for any other use cases you have. So at that point, at query time, all you have to do is read the value from the index using the field value feature. So we did this, and we were hopeful. We deployed, and this is what happened again. So again, we had this horrible spiky white line. So what this meant was that we couldn't really go forward with this. We had to roll it back. So why was this happening to us again? So we knew straight away what was going on, and it was the fact that reading from the index could still be slow, particularly when you're doing it using stored value fields. So we went in and we changed the implementation of the field value feature to use doc values when they're available. And the good thing about doc values is because they are column-oriented, mapping doc IDs to values, they're much faster for this particular use case. So we did this, and as soon as we changed the implementation from stored values to doc values, okay. Is anything else going to happen today? Okay. All right. So we were going 5 times faster, taking 25 milliseconds to compute features on 100 documents. So were we there yet? So we had nailed the feature logging and feature computation bit, but we hadn't even looked at what was happening in the re-ranking part. So at that point, we introduced the notion of a no-op model. So this was a linear model that would perform all the computations, all the operations needed to do learning to rank in production. But it wasn't actually changing the search experience because we were only applying a non-zero weight to the Solr score, which was what we were using to store documents to begin with in the first retrieval step. So this was just something for us to test the stability and the latency of the infrastructure. As soon as we did that, we saw that without learning to rank, if we were retrieving 3 documents, we were taking 39 milliseconds. As soon as we switched learning to rank on, we were taking, and we ranking just 25 documents, we were taking 77. So almost twice as much. So why was it slow again? So to give you some context, in the new search engine of Bloomberg, we have to use grouping. And we have to use grouping because we ingest stories from many different types of sources. So what we don't, and we often end up having stories that are almost the same, so duplicates. So we don't want to clutter the user screen with stories that are about the same thing or just exactly the same. So we use grouping. And the problem is that grouping and re-ranking is not really a match made in heaven. So just plain old grouping is expensive. You need 3 communications rounds between the coordinators and the shards. One to get the top groups from each shard, another one to get the top documents for each group from the shards, and another one to get the fields. With re-ranking, this is even worse because you have to re-rank the groups, and then you also have to re-rank all the documents in all the groups again. So it's painfully slow. So at that point, what this meant was that we had spent all of this time optimizing all sorts of things, months agonizing, but unless we had actually fixed this problem with grouping plus re-ranking, there was no way we could go to production. So the road to production was blocked. So instead, we went somewhere else.
So we were really desperate that we were not able to reach the performance that we needed to run learning to rank in production, but they decided to go to Las Vegas. It was not to play our money at the casino and go for a better life, but it was because last year the version of Activate or Lucene Solar Revolution was in Las Vegas. So we were actually going to the conference to attend, and we were on the flights, and we were talking about these problems, and while we were talking, we had an idea of how to fix the issue. And we started to code a prototype on the flight, and that's why the patch that we proposed in the Jira is called Las Vegas patch, because we were going to Las Vegas when we wrote it. And I'm going to explain briefly how this thing works. So as Malvina said, like grouping is painful. It's painful normally when you don't do learning to rank. It gets more painful when you do learning to rank. At the moment, it's not supported. We have a patch also to have learning to rank and grouping work together. But it's painful because you need 3 communication rounds. The first round, the federator asks for the top groups to each shards. Then he gets the top groups, he merges them together to compute the top n groups among the shards. Then he sends back the top n groups, global n groups, and asks each shard to return its top n documents for each group. And then he gets back the results. He computes the top documents among all the shards. And then there is another round to get to just extract the fields for the documents. Okay? So step 1 and 2, they are 2 complete Lucene queries to the index. Okay? So it's expensive. And why you need to do 2 queries? Here there is an example. So we have machine 1 and machine 2 contain different documents. And we are asking for 2 groups and the top 2 documents for each group. And I don't follow these, like, trust me. These are the results that each shard will return. And if we just merge these 2 results from the shards, we get these results. So we will have group 1, top documents 4 and 1, and group 3, top documents 6 and 8. Okay? And this is wrong, because we have this small document here in the second shard that is in group 1, and has scored 50, while document 1 has scored 20. So we are not returning the exact result for this. And we are not seeing these documents because it's hidden by the other documents that this shard is returning in the first round. So that's why you need another round to ask each shard to return you the top documents for each group. So the idea behind the Las Vegas is quite easy. You have this problem only if you are looking for more than one document per group. Because if you just want the top document of the group, at the first round, you have it already. It can change, okay? So given this, we just patched Solr to skip the second step completely if the query was asking only for one document per group. So there was some things to change in how the communication was happening, but it was possible. And this made easier also the learning to rank part, because we were doing learning to rank only once instead of twice in the process. So we finalized our patch. We rolled it out in production, and we started to test it only like in the normal search settings without learning to rank, okay? So and this is what happened. The normal search with grouping was taking 200 milliseconds in median time. And when we enabled Las Vegas, it started to take 120 milliseconds. So we had a speed up of the 40%. Was quite happy with that because we were saving a lot of time. And then we say, OK, now let's enable learning to rank with nought model. And these were the final performance. So with learning to rank and grouping and Las Vegas patch, median time was 180 milliseconds, a bit slower than just Las Vegas because we were doing learning to rank, but still faster than the original ranking that we were doing. So we pushed learning to rank in production, and we also saved 20 milliseconds out of that. So we were good with the performance, and then we realized that we were so busy focusing on performance and on making it faster enough that we didn't think about the model. So we had some models, but we were not really sure about that. So we started what we call the Learning to Rank hackathon. We spent weeks just writing code to process our data and put them in a nice SVM-like format. That is a format that is accepted by many Learning to Rank library. And then we wrote wrappers around scikit-learn to train different type of models, do regularization, hyperparameter optimization, a lot of buzzwords, and to do model debugging, so to see actually how it was going. And then we went through an evaluation. So we had the metrics that I was telling you before, mean average precision, NDCG, and MRR, that is another similar way to compute NDCG. Together with that, we also evaluated the model with people expert in the domain. So people expert in the product that know what people in use expect to see. And when they say that it was OK for them, and we saw that we were good with the metrics, we started to roll it out in production. We had a very slow rollout. We released initially only for some people inside the company, then to all our internal users, so also to the newsroom, the journalists. And then we monitor, and we saw that it was fine, and then we go for 10% of our clients, and then 100% of our clients. It's been on for several months now, and nobody complained. So we, we assert that it's good. And then that's all. It's a new learning to rank world now. So now our job basically consists in trying new feature that we think might be interesting for ranking news, experiment different type of model and different way to produce training data, and rolling out. So rolling out new rankers and check if they perform better or worse. We also work on different type of queries. So you might have different type of queries and different models according to the query. If someone is looking for a company, it might be different than if someone is looking for a country. That's all. So take-home messages. The first one, always measure, always be sure that you have metrics to measure if you're doing good or not. We made an error at the beginning because we wrote everything, but we didn't have measure to say if there was a feature that was slow. So in the moment that we had performance issue, we had to spend time by writing code to measure the performance and then roll it out again, and we lost time by doing that. We should have thought about that at the beginning. So always have metrics. Second lesson is more basic in this. If your feature is static, it's a good idea to put it in the index. It's not going to be too much expensive in terms of space. It's going to save you a lot of time. And also, like, if you index the feature, make sure that is a doc value, because reading from the disk is expensive. And the last, if you are not happy with the performance of your search, you should go to Las Vegas, because you might end up improving the performance of your search engine by 40%. So thank you. And by the way, like, we have an open position for a senior engineer to work on Relevance. So if someone of you wants to join us, please apply. This is the link. Thank you.